Yes, as Chris said, I realized it's the 100th anniversary of Appleton's experiments, which led to the discovery of the ionosphere. And I can't think of a better place to be celebrating this. But I want to go into the context of the time, really. So in 1901, Marconi conducted his famous experiment where he transmitted the first transatlantic radio signal. To give you an idea of other things that were happening in 1901, I've just had a look on my phone. It was the first invention of the safety razor. Hubert Booth invented the vacuum cleaner. Queen Victoria died. That was third on the list. And there was no mention of the discovery of the electron or the discovery of X-rays. So I think the AI on Google has got a little way to come before it knows what answers it needs to give me. But anyway, so this is Marconi's transmitting station at Poldhu in Cornwall. And you can see the interior here, the transmission. And there was initially a circular array of antennas. They blew down in a storm, apparently, and so they had to erect fewer antennas. But you can look on Google Maps now. We've got to make it a space talk. And you can still see the shape of the Marconi's original array. And this is that building you saw there now, sort of rotting into a field. So I think it's probably ripe for a bit of archaeology now. But what was so remarkable about Marconi's experiment in 1901 is that it couldn't really have been possible. So if we go up from Poldhu, he and some colleagues set themselves up at a place called Signal Hill in Newfoundland over here. And they arranged at a known time to broadcast a known signal. It was the Morse code S. And in terms of blind experiments, that's pretty terrible because he knew when to listen for it and he knew what he was listening for. This is where he was. I don't think the car park was there then. But if we go up again from Signal Hill and take in the actual path that the radio signal had to have taken, it's about 3,600 kilometers. And it really shouldn't have been possible because it would have had to have gone around the world. And we knew that radio was a form of light and that light travels in straight lines. So there's two possible ways that this could have got there, the theories of the day. So you broadcast your radio signal, it goes out in all directions, but there is a component of that which will head towards Newfoundland. But it will go in a straight line and it won't go through the Earth, so how did it get there? Well, some people theorized that somehow the conductivity of the ocean was helping to bend the signal around. But there was also a theory of a radio reflective layer put forward by two people, Kennelly and Heaviside, which was saying that there could be electrified particles in the upper atmosphere which would resonate with those radio waves and enable your signal to arrive at its location in Newfoundland. So this experiment had happened. People knew that this was possible, but they still had no proof that there was this radio reflective layer. And Appleton published this paper, or rather he submitted it, October 14th, 1925, discussing an experiment that he had done, for which he was later cited and won his Nobel Prize. So I want to give everybody hope here that you can, if you find your niche, you can get a Nobel Prize for quite a simple but elegant experiment. So in his paper, he says that there's several things that you need to be able to explain about radio propagation. Is why will it go around the horizon, and why does it suffer really rapid variations in signal intensity? And he talks about Smith, Rose, and Barfield having a paper out which says that both of these can to some extent can be explained by the presence of this Kennelly-Heaviside layer, but it's generally admitted that further evidence of the existence of the layer is needed. So Appleton set out to do this. Now, his research area was he was interested in why radio signals faded in and out. And his theory, which proved to be correct, was that if you had two radio signals, radio is a form of light, and so those, if they meet and the light waves are out of phase, you can get constructive, destructive interference, and so your radio signal will fade in and out. And as a teenager who grew up listening to the American football from the American Air Force's base in Germany that were broadcasting it, very frustrating, it tended to fade out at just the wrong moment. So this is what Appleton did. He arranged for some colleagues at BBC, the British Broadcasting Company as it was then, in Bournemouth, and so this is a place close to my heart. I grew up near Bournemouth, and so this is a bit of a rabbit hole, bit of a side, but there was actually some footage here of the researchers coming in and out of their hut at Bournemouth, and you can see it was nothing much more than a hut, really, with a giant antenna on the top. And if you fancy a sing-song, this is the Bournemouth calling tune that they used to go out every morning in the 1920s. But there's very little exists of the Bournemouth facilities now. So Appleton wanted to use Bournemouth because he noticed in his experiments that you had the greatest fading when the path length between your transmitter and receiver was about 100 kilometers. So he set the Bournemouth transmitter as his transmitter and set his receivers up in Oxford. And these are the plans of where the radio BBC Bournemouth was. It's on the edge of a housing estate of bungalows, and growing up in Bournemouth, that's a feature that I'm very familiar with. And it's on the very edge of the cemetery. So again, we can use Google Maps here to show. I think Les Dawson is quoted as saying that Bournemouth, he described Bournemouth as a cemetery with bus stops. And I don't think this does much to disabuse you of that notion. But this is where BBC Bournemouth was. It is now, of course, a row of bungalows. And we can now, hold on to your chairs, this is a bit of a dizzying one. We can now go from Bournemouth and head across country with the radio wave to Oxford. Wave at us as we go by, we're there somewhere. And the signal was received in the electronics lab at the university. Here we are. Oh, it's really difficult, this close up. So here we are. This is where the signal was received. But we can show again by zooming out with the magic of Google Maps how different an experiment this was and how useful it was to get those scale sizes just right. Because now, if we go to look at the ground wave, we'll be propagating across that sort of distance, and the sky wave reflected off the ionosphere will be coming down over that sort of distance. So you receive both of those sort of distances, and he had arranged for the engineers at Bournemouth to broadcast a signal just to carry a frequency. There was no program being broadcast, but this to gradually change the frequency of that signal. And by doing so, he came up with this expression here. N is the number of times your signal will fade in and out, and the lambda is the two wavelengths. And just looking at this path here, path along the ground A, path by the ionosphere is A dashed. And from that, he worked out from the number of fringes that the height of the ionosphere was 100 kilometers. Now, really interestingly, in this paper, he doesn't actually publish any results. He just says, this is what we found. I don't think you get a paper past peer review now, but Appleton clearly had a bit of clout. So he had shown that the height of the ionosphere was around 100 kilometers, and this was mentioned in his citation for the Nobel Prize some decades later. But almost simultaneously to this, two scientists in America called Breach and Tuve, and I apologize for the pronunciation, I've only ever seen their names written down, they had actually worked out how to send radio pulses, very short pulses up into the upper atmosphere, and from the time delay of those echoing back, they too had worked out that the ionosphere was about 100 kilometers. Well, Appleton, unlike those, they thought this was interesting, they left the field, they didn't do anything more. But Appleton took their technique, and he and his colleagues at the Radio Research Station at Ditton Park in Slough, and here it is. I do have a hankering to do a documentary one day called Men in Their Sheds, because this basically was what was happening at Ditton Park. But Appleton's hut was this one here, Hut 18, And you can see again the big radio mast on the top. And by broadcasting an increasing a series of frequencies that again were pulses of different frequencies, you could gradually probe higher and higher through the ionosphere, and you could create vertical profiles of what the ionization was and what layers were happening. And so here are some of the first scans that they made in a continuous sequence. So it's frequency along the bottom. Confusingly, it goes from right to left in these ones. And effectively, it's height at the top. It's the time of flight of the radio wave. But that's not quite the same as height, because the layers underneath slow your radio wave down as it goes. But this is now continued today at the Rutherford Appleton Laboratory. And here is a sounding from only a few days ago. We have at the back there a display showing you the real time ionospheric displays. And this is the longest continuous sequence of ionospheric data in the world. And it's incredibly prestigious. Everybody who's doing any kind of ionospheric science uses the Slough-Chiltern data set as their reference. And my supervisor, Henry Rishworth, used to say that for about 20 years, when people talked about the ionosphere, they meant the ionosphere above Slough. But we now know a lot more about this. So here we have the solar activity at the top with sunspot numbers. So that gives you some indication of the solar emissions, these extreme ultraviolet and X-ray emissions that are being absorbed by our atmosphere, which is creating this ionization. And you can see that the Slough-Chiltern sequence follows those very closely. The second longest sequence in the world is at Port Stanley in the Falkland Islands. Unfortunately, it's proving quite tricky to find the funds to keep that one going. Stanley's in a very interesting place because it sits very close to that South Atlantic anomaly. So there's probably some interesting science going on that we're missing because we can't make the measurements there. But these data are still in demand. People, they go into all kinds of data products that help companies to produce maps of radio communications. People are still using HF radio for between aircraft, between mountain rescues. The military use HF radio. So this is still an important thing to be measuring. But there's also much else in this data sequence. These data are unique. They're priceless. We know that there is a climate change occurring. And this is Ed Hawkins' visualization of that as a climate spiral. And around 1999, I think it was, Henry Rishworth wrote a paper, well, if this is happening in the atmosphere, we should see it in the ionosphere. If you're trapping heat in the lower atmosphere, Roble and Dickinson, these two scientists from America, they showed you that actually the upper atmosphere will be cooling and contracting. It's very difficult to make a direct measurement of the upper atmosphere, but sitting within that is this radio reflective ionosphere. So we've got lots of measurements of that. We've got measurements of that since 1930s. That gives us a whole atmosphere measurement of this, so it should be possible. So we go and do it. The thing is that with those soundings we've got, they would just mark the peak frequencies, certain frequencies. It's quite a lot of complicated information. So the only way we can do it easily with this long sequence is by using an empirical formula that people had used for estimating the ionospheric height for radio propagation. And if you do this for Port Stanley, you do see the ionospheres coming down. For Slough, it's going up. And that's because the formula breaks down. It's not taking account of that underlying ionization. So what we need to do is to go back to those original data and scale it. There's also information about what's happening in the lower atmosphere. So we can see here, top left, the ionosphere is intensified as a result of lightning. And we also did a study which showed that the European bombing, the Allied bombing of Europe, had a detectable signal in this Slough data. So it's detecting stuff from below. There's all kinds of astronomical stuff in here too. There's lots of solar eclipses and meteor showers. These are all going to be recorded. This is some work we did from an eclipse in 2015. We now have spacecraft observation looking at all these different wavelengths. We can work out which wavelength it is that's causing this variation. And as it eclipses these active regions, you can see sudden drops in the state of the ionosphere. We can use this data to look at the X-ray emissions of the sun from decades before the space age. Some really interesting science to be done there. And the thing that's dear to my heart, has been mentioned several times in the room, is space weather. And we had a big space weather event in May this year. This is the ESA SOHO spacecraft showing the mass ejection, all those particles hitting the detectors of the spacecraft on its way to Earth. This is a rather giddy space scientist in a field just up the road as the skies lit up. I had just come out of the pub, but I don't think it was that. And you can see the effect it has on the ionosphere, all kinds of strangeness. And this ionization at night shouldn't have been there. This is the radar seeing all the particles coming into our upper atmosphere. I want to preserve this archive. It currently resides in a basement here at RAL. It's on something like 250,000 pieces of photographic paper. Each one of those is unique. If that's lost, the data are lost. So we are proposing to try and scan these. Matthew's got some scanners that take enormous bits of paper. And we've shown that it is possible with other data to set up citizen science projects where you serve these data to interested members of the public, and they will spend time actually identifying features on there for you. So we would really love to capture this data because it contains so much more than just the state of the sun. It tells us about the lower atmosphere and whether there's any long-term change going on. So thank you very much.
Any questions for Chris? Yeah, go ahead.
How big an effect did the bombing have that they detected, and what exactly was going on there?
Crikey. The big bombs that we were dropping, the blockbuster bombs that we were dropping on Europe during the Second World War, created shock waves. Those shock waves, as they travel up through the atmosphere gets thinner, so the amplitude of those waves grows. They eventually break in the upper atmosphere, and that heats up the atmosphere very slightly, and that changes the chemistry a little bit. So it lowers the intensity of the ionization just temporarily while until that heat is dissipated.
What was the high frequency component in the time series data you showed? It looked like 15, 20 peaks per year?
The very, very long one. So it's an 11-year cycle, and superimposed on that is an annual cycle. But excuse me, I haven't turned my mic off, shouldn't be coughing into you. The Port Stanley shows a semi-annual variation, and that's to do with the different chemistry of the atmosphere in those two regions.
So you've got your citizen science project to get data out of the archive, but what about preserving the archive? I mean, yeah. I guess these things are quite fragile now. And it's a little bit like some of the problems we have in astronomy. We've got records going back centuries in astronomy. And they're very hard to access because they're on paper. Yet we don't have any funding to actually convert them into more modern storage areas. Have you got any ideas about that?
Yeah, I mean, there are precedents. So the Hurstman So archive of solar observations went to the University of Cambridge, who are now curating that. That's really good. The data exists, but it doesn't make it any more accessible necessarily, because you then have to have access to the library. So I would like the physical things to be preserved at some point, but prior to that, I would like to try and digitize them so that we can make the information available to the science community.
Maybe we should have a national project to digitize these archives across the board.
Yeah, this is our heritage, yeah.
Thank you. Any other questions? Yeah, go ahead. Maybe a different speaker. I'll come back to you.
Thank you. I'm not wishing to be controversial here, but obviously the Earth is warming up. It's been warming up since the start of that particular record. Yet I see that there is actually an acceleration. It seems to me that there is an acceleration in Earth warming over the past, I don't know, 25 years or so. It seems to be real, the acceleration.
I won't be saying no, but I believe one of the other speakers in this session might have something to say about
that. That's
cool.
Thank you.
Okay, yeah, maybe one last question.
Given that this data is hard to access and hasn't been digitized, how have researchers been accessing it so far? You said that people refer to the SLOW data.
So they're looking at the key parameters that have been scaled off these data. But if you go back to those original soundings, they contain so much more. It's just that back in the 1930s and 40s, representing all those data points of the height profiles was kind of too time consuming. So it was done occasionally, but it's the scaled, the key parameters that have been taken off that people are referring to. That's all they've got access to at the moment.
Right.
I think we have a question online, or
Yeah, just a quick question. You talked about using a citizen science project to pick out interesting features of that data. Is there any prospect of using an AI to pick out interesting features of that data, which I guess might be quicker, but is there a problem with training data, that sort of thing?
That's a really good question. In fact, there has precedent been set with some of the astronomical citizen science projects where they have used human classifications to train the AI. And I think there is a potential for doing that with these. The problem is, and I'm speaking here as a scientist, that scientists like to tinker. So there's no standard format for these ionograms. They gradually evolved as they got better and better at doing it. So you'd probably have to do it in chunks so that you could train on each type of ionogram that the thing was returning. But you'll notice that these don't have axes on them. Again, if one of my students gave me this graph, I'll give them a ticking off for that. And it's because it's a piece of paper that's being wound by a clockwork motor past an oscilloscope screen. This is an analog way of creating a graph from an instrument. And we have the Rosetta Stone on the wall at the back there, which is some ionograms that they put up at an exhibition in the 50s, where they've drawn on what the axes were. So we have a way of knowing what frequencies. Each one of these vertical lines, by the way, is a radio transmitter. So they also contain information about the broadcast history of the early BBC and other broadcasters. So there's so much information in here.